So we can start. Please, if you're online, indicate that you are online. If you're online, indicate your presence, that you are online. If you're online, indicate that you're online. Please indicate that we can start. Please, if you are active, indicate that you are active. If you're online, indicate your presence. So we can quickly start off this class. Good evening, guys. Please, if you're active, indicate your presence that you're active, because we're about to start tonight. Please indicate that you're active. Okay, good evening. Good evening. Sarah, you're welcome. Ugochi, you're welcome. All right. Melon, you're welcome. Okay, Franklin Charles, you are also welcome. Thank you, guys. Okay, let's just start straight away, but then we don't have much time. This class will just take us like an hour, all right, so that we can meet tomorrow. We'll keep on meeting throughout this period. So today is public holiday here in Nigeria. For those of you who are watching us outside the country. All right, we started a journey under electrostatics. If today is your first time this semester, please go through our previous videos, okay? Because there are some things we discussed there, of which I will not be repeating, because we should be progressing, not going back to previous classes. But I'll give a brief introduction so that we can have an idea. In our previous class, we talked about electrostatics. That the word electrostatics means the study of charges at what? At rest. The word static talks about rest. The word electro talks about electric charge. So the study of electric charge at rest is called electrostatic. And we have two types of charge. We have the positive charge and the negative charge. We also have what we call a neutral charge. Then we define the positive charge as a charge that is electron deficit, meaning they lack electrons in them. That's why they are called positive charge. Then the negative charge, these are charges that are electron rich, meaning they have electrons. An example of positive charge, we said we have proton, right? Example of negative charge, we say we have electron. Example of neutral charge, we say we have neutron. Is that not? Which is neutral. Then we proceeded to the properties of charge. That we say charge is quantized. Electric charge is quantized, meaning that number of charge is equal to what? Ne, where N represents a whole number, E represents our electron, which is about 1.6. Electron represents minus 1.6 times 10 to the power of minus 19 Coulomb, 1 electron. The N represents our whole number, which can either be 1, 2, 3, or 4. This means that electric charge is quantized. It means it is fixed. That means the charge in here can either be a multiple of 2, a multiple of 3, a multiple of 4. If it's a multiple of 2, that means we have 2e, right? Number is there is what? Is 2. Our electron, which is 1.6. If it's a multiple of 3, that will be what? 3e. We can have 4E, we can have 5E. All of these represent that electric charge is quantized, which is the first property or the first characteristics of electric charge. Then we'll say that electric charge um, cannot be created, right? Not destroyed, but can be transferred from one point to another. We can transfer them. I will give a good example when we rub a comb on our hair. When you rub your comb on your hair, what is happening there is that the air is transferring what? A negative what? Charge, making the comb negatively charged, then making the air will remain positively what? Charged. This is the reason why the comb itself can be used to lift a piece of paper. All right. Uh-huh. So the study of such kind of charge is called what? Electrostatic. We talk about another property that says like charges repel each other while unlike charge attract. When I say like charge, if I have a negative charge with a negative charge, once these two comes together, there must be a repulsion that will repel. If I have positive with positive, they also repel. But if these two charges are unlike, let's say we have negative and positive, what will happen is what? They will attract. So unlike charge attracts, while like charge repel. These are properties of what? Electric what? Charge, and so on and so forth. Then we now talked about Coulomb's law, where we stated that Coulomb's law is force equals to K Q1 Q2 over what? R squared. That if we have 2 point charge separated by a certain distance R in meter, right? We can be asked to find the force that acts between them, or the force that acts on a particular point charge over the other charge. All right. And we say that according to Coulomb says that force of attraction or repulsion, which is also called the electrostatic force, all right, between the 2 point charges, the force is directly proportional to the product of the charge. That force is that proportional to the product of the charge, meaning Q1 times Q2. Okay, the force is what? Directly proportional to the product. This is a direct relationship. In variation in mathematics, we have types of variation. We have direct, indirect, we have inverse, right? We have joints. Is that not? We have partial. But for this is called what? Direct, meaning that the more the charge is, the more the force of attraction or repulsion. If I should increase this charge, the force here will also increase. That's the first Coulomb's law. The second that says that same force is inversely proportional to the distance of separation between the 2 point charges. This is their distance here. An inverse relationship is a negative relationship. What do I mean by negative relationship is that as the distance is increasing, that force will reduce. Logically, the more we bring these two charges together, the more the force of attraction or repulsion will increase. So increase in distance reduces the electrostatic force. So we are saying that force is inversely proportional to the square of the distance separating the two charges. So when you multiply the first equation with this, that will give us our force proportional to Q1, Q2 divided by what? R squared. Is that clear? So in mathematics, we have been taught that if we are to remove this sign of proportionality, we have to introduce a constant called K, right? So by the time we remove this, I will introduce a constant, also introduce an equal sign here. That will give us force equals to K, Q1, Q2, divided by what? R squared. Where K, we define K in our last class as, we define K as 1 divided by 4 pi permittivity of free space. K is defined as 1 divided by 4 pi permittivity of free space. Permittivity of free space which is about 8.85 times 10 to the power of minus 12. Okay, farad per meter, F per meter. This is the value for the permittivity of free space. But although the value of K by calculation is given as 9.0 times 10 to the power of 9 Newton meter square per Coulomb square. Take note of this. The value of K is 9.0 times 10 to the power of 9 Newton meter square per Coulomb square, while the value of our permittivity on the board of free space. We are dealing with free space. We are dealing with vacuum, or we can say permittivity of air. We are considering the atmosphere here to be what? A free space, separating the two charges. All right. So we have permittivity of a material. If I have a material here that fill up this space here, we'll be considering the permittivity of that material. But because we are looking at the permittivity of air or of free space, the value is what? 8.85 times 10 to the power of minus 12. So this value is simply for that of what? Free space. All right. So these are the things we discuss. Then we now say that Coulomb's force is a vector force. Of course, force is a vector quantity that must have size and what? Direction. So we say that instead of having this expression as a formula for Coulomb's force, the formula becomes, let me get our duster. The formula becomes F equals KQ1 Q2 over R squared times unit vector. This value represents the direction. What we have here represents the magnitude of the force, of this force. This represents what? The direction. In our previous class, we talked about this. Please go back and watch the video. I won't be talking about the direction of action. We learned something called, a topic called direction of action. Direction of what? Of action. I introduced this in my previous class. You can't get it anywhere. You can't get this anywhere. I'm saying this live. Please go back and get it and get the video and watch. Why it is still up? It is still in my channel. All right. So please make sure you watch. Now let's proceed to electric field intensity, which is the major thing we shall be discussing tonight. Electric field intensity. When you hear the word intensity, what comes to your mind is strength, right? Electric field what? Intensity. Intensity of a field. Electric field intensity talks about the strength of a field. The strength of a field generated by a charge or a system with multiple charges. For example, let me explain what I mean by that. We have seen that charge can be quantized. Charge can be either this, can be either 2e, can be either 3e, can be either the what? 4e. Are you there? If you look at this, the value of E here is increasing, meaning the intensity are not the same. Here we have 1 electron, we have 2, we have 3, we have what? 4. The number of field lines that will be generated by each of these charges can never be the same. Let me explain what I mean that. Let's say I have a system that has just +1 charge. Don't forget that positive charge produces lines of force that tends to move what? Outward. Lines of force moves what? Outward for a positive charge. If it's +1 charge, this +1. If I have another system, let's say I have +2. What do you think will happen to line of force? It will definitely double itself, right? It will double itself. Instead of having 4, we're going to be generating its lines of force. Immediately we increase this again, it will increase. That means the more we increase the charge in a particular system, the more the lines of force, the more the strength. If I'm to ask between this system A and B, which of them will have higher strength or will have more intensity? Okay, which one will have more intensity? Definitely is this, right? Because we have more fuel lines here. Any test charge, please, if I have a distance, let's say the distance here is 1 meter, and I place a test charge Q naught. I have the same distance, 1 meter, and I place another test charge what? Q naught. Which of these will experience more intensity? Is this test charge? It's like saying having a burning bush. I always give this example. If you have a burning bush, a bush that is burning, if you come close to that burning bush, you'll feel the heat. You'll feel the intensity from the burning bush. Exactly. Now, what happens if you add more fuel or more kerosene to the bush? It will increase the fire. You will feel the intensity as you increase, as you add more fuel or kerosene. That's what happens to charge here. If we have +1, we have fuel lines. If I'm to increase the intensity here, what do? I will increase the charge distribution or the amount of charge. So by the time we add more charge, we are increasing the intensity. So any other charge or test charge placed close to this test charge, we experience what we call what? Intensity. We experience the influence. Intensity is not experienced on the point charge. We call this point charge B, right? This is called what? Point what? Point charge what? Point charge A. Intensity is not experienced at the point charge. The burning bush cannot tell how intense it is. It is the individual that comes close to what? The burning bush. So it is the test charge that experiences the intensity, not the charge itself. Am I communicating that? Now, one thing you notice that any charge placed around any of this system, right? We experience what? Force, a force, according to Coulomb's law. And that force will be directed towards, the force will be directed towards the test charge. Towards what? The test charge. All right? Now, let me explain what I mean by that. Just take note that let's look at, please, if you are following, indicate in the comment section that you are following. Let me know those who are following. Let me know those who are following, please. If you are following, indicate that you are following. Please, if you are following, just indicate that you are following. Let me know so that we can proceed. So we have some explanation and some derivations to look at. And please, if you have not liked the video, please like the video and share the video now. Share for more people to join us. Please share. All right. Please, let's share the video. Let's reach out to other people. Now, I want to establish one or two things here. Guys, listen. Let's say we have a system of charge here. Dot. Let's say we have this. This is a charge, all right? And we have separated by distance out a meter, and we have a test charge. We call this a point charge, right? This is called a test charge. Okay. Now listen. Intensity is simply defined as force per unit charge. But let me explain what happened here. You must note that for electric field intensity, the force experienced between these two systems of charge, that force experience is proportional to the intensity. Meaning, the more we increase, the more we increase the intensity, right? The more the force will increase. For me to increase the force of attraction or repulsion between these two, I have to increase the amount of what? Charge here. This also means that, or I can rewrite this let me rewrite it by saying that intensity is proportional to force, right? Or the same thing. This will give us equation. This is directly proportional. The same intensity is proportional to what? To charge. So what? To charge. Are you there? Now, by the time we combine these two, that will give us our E is proportional to what? To FQ. Okay? To FQ. Please, if you are following, please indicate that you are following from the comment section. Hello, I think the network is very bad. Network is so bad. Network is so bad. Network is so bad. And are you guys following? Network is so bad. I have to, a call came in my device, so that's interrupted the network. I have to just end the call. I'm so sorry for that interruption. I'm sorry for that interruption. Please, I'm sorry for that interruption. Now let's proceed. Now listen, we are saying that intensity is what? Proportional to what? To force, right? Intensity is also proportional to what? To charge. Okay, by the time we combine this, but let me show you something. I think there's a little alteration here. Listen, look at this. We are saying that intensity is proportional to what? To force. Charge. I can as well write this. Let's rewrite this as, sorry, I think the first way is the best. Force is proportional to what? Somebody intensity. Is that clear? That same force is proportional to what? Somebody to charge. Let me explain this. This is the right expression here. Look at this. The more we increase the intensity, the more the force will increase. Is that not? The more the charge increase, the more the force will also increase. This is the right relationship here. The other way is still correct, logically is correct, but this is the right way because I want to derive an expression for electric field intensity. So force is what? Proportional to intensity. The more the intensity, the more the force. Meaning, if I'm to increase the amount of charge here, it will increase the amount of fuel lines, right? And by the time the fuel lines increase, the flux, the electric flux generated here, electric flux generated here will also increase. So that means that the force of attraction between this and this will also increase. Now, also, if we should increase the charge here, it will also increase for somebody, the field. So these two, they are almost the same in relationship. So that means that if I'm to call this equation 1 and this as equation 2, let's find what will be the force. Then, by the time we combine, it means I will look for what is common between them, right? Which is our force. So force is proportional to QE. What happened here is that we multiply E by Q, and that gives us this, right? In mathematics, for us to remove this sign, what do we do again? I have to introduce a constant. So F is equals to what here? K, Q, E. All right? Now listen, to define the force, this is undefined. I've not defined my force yet. Okay, to define the force, I have to say let K is equals to what? 1, equals to unity. So if K is equals to 1, that simply implies that our force becomes equals to what? Q what? Somebody? QE. So from here, we can make our E as a subject of the formula. I can divide both sides by, can say divide both sides by what? By Q. And that will give us force over Q equals to QE over what? Over Q. From here, Q can go with Q, yeah? Then our intensity becomes what? Force over what? Over charge. So what do we intensity as? It is defined as force per unit what? Charge. Force per unit what? Charge. Intensity is defined as E is defined as force per unit charge. Unit charge. Okay. Force we know is measured in Newton. Charge we know is measured in what? In Coulomb. That means that the unit of intensity becomes what? Newton per what? Per Coulomb. All of this, for those of you who are post-UTME students or JAM students, you don't really need the derivation. All you just need to know is the unit of what? Intensity. But for those of you who are in IMSU State University, you have to take note of the derivation. You might be asked to prove why E is equals to, why do we say E equals to force over what? Charge. I've only shown us that the first step is that your force is proportional to your intensity. Increase in intensity leads to increase in force. So whatsoever happens to intensity is caused by what? By charge. So increase in charge is also what? Also leads to increase in what? In force. So these two exist. So by the time we combine them together, that will give us this, right? Then to define the force, well, we're going to say that let K equals to 1. If K equals to 1, meaning that our force equals to what? QE. Then we divide both sides by what? By Q to make our E a subject of the formula. And that gives us our intensity as force per unit charge. All right? Okay. So let's proceed further. Now we have defined the word intensity as force per unit charge. The intensity talks about strength, talks about the amount of few lines that emanated from a single point charge over the influence of force. Another word, charge. All right. Okay. All right. I want to take us to a little journey. Let's look at some cases. If let's consider some cases between two charges. The first case I want us to look at is a case between 2-point charges. Let's say we have charge 1 and what? Somebody, and charge 2, separated by a distance what? M. You know, we define that intensity is equals to force per unit what? Charge. Meaning from this relationship, we are saying that intensity is what? Proportional to what? To force. Meaning that if we increase our intensity, that will also increase what? The force. I mean, whatever happens to intensity must happen to force. And force is a vector quantity. So that means that if force has magnitude, right? And what? And direction, it means intensity must also have what? Magnitude and what? And direction. In other words, force is a vector quantity. Intensity is also what? A vector what? Quantity. Are you there? So when you talk about intensity is always experienced by a test charge. Like I say that the point charge does not really experience the intensity. If I have a burning bush, the burning bush cannot determine its intensity. Intensity can only be determined when you place a test charge, right? Now, we are looking at a case here where we have charge 1 and what? Charge 2. Let's assume that charge 1 is the point charge. We are assuming that charge 1 is the point charge, and here is what? The test charge. Now, which of these do you think will experience the intensity? Definitely is the charge 2. Because charge 2 is the test. Test charge is used to know the amount of force or few lines that emanated from what? The point charge. So for me to test the intensity in this system, I have to use a test charge, right? If the equation emphasizes that find the intensity on charge 2, that means that the intensity of charge 2 can only be gotten from where? Somebody charge 1. Or I repeat again, if the question says find the intensity at what? Charge 2, that means charge 2 becomes the test charge. If the question says find the intensity at charge 1, that means charge 1 becomes what? The test charge. I'm not saying that all the time that charge 1 must always be a point. It depends on the emphasis given in the equation. If the emphasis is on charge 2, you must have to take that charge 2 as your test charge. If the emphasis is on charge 1, you must have to take that charge 1 as what? Your test charge. Sometimes we can even have another charge here in the middle. Let's say charge 3. And they will say find the intensity on this charge. Alright? Now let's watch and see. Note that recall that intensity is given as what? Force per unit what? Charge. Meaning, if I have two charges separated by a distance, let me take off this point first. Separated by a distance, the intensity experienced in charge 1 is equal to what? Somebody force over what? Q1. Intensity experienced in charge 2, what would that be? The same force over what? Q what? Q2. Why did I say F1 over Q1? No, because if I have an intensity here, the same force is experienced along this line here. So we don't use F1. You can see that even under E2, I didn't use F2. I have to use F because the same force is experienced. So if I'm to find my intensity in charge 1, formula says what? E1 equals to what? F over what? KQ1. But recall that Coulomb force says what? K equals to what? KQ1 Q2 divided by what? R squared times unit vector. Alright? Most of us in secondary school, we are only familiar with this, without this, just this alone. I say this in my previous class, that Coulomb's force is a vector force, and every vector must have magnitude and what? Direction. So this is the magnitude, this is direction, right? And in my previous class, we analyzed how to find the direction of action, which is our unit what? Vector, right? Now listen, if Coulomb force is this, can I replace my force here? Let's call this equation 1. This is what? Equation 2. So let's put equation 2 into equation 1. By the time we put our equation 2 into equation 1, this will give us what? Let's go. Our E1 equals to our force over Q1. What's our force again? The whole of this, right? That will give us what here? KQ1 Q2 over what? R squared. Exactly. Dot unit vector. Here we have divided by. So let me use the division sign here. By what? By Q1. Don't forget, our E1 is force over Q1. Our force is this, right? Of which I have to substitute here. So this is my force. Our force is this. And we are told that that same force is divided by what? Q1, which is this. Okay, so by the time we solve for that, in mathematics, if I have division sign and I'm to take off this sign to put multiplication, what will it be? With times, I will then have to inverse this, right? This will give us what here? 1 over what? Over Q1. Are you seeing it here? Okay, let me leave it for teaching sake. So divided by what here? By Q1. So by the time we take off that, what will be the result? What will be the result? Our E1 will then be what? K Q1 Q2 over what? r squared times unit vector, then multiply with 1 divided by what? Q1. Q1, we go with Q1. So our intensity experienced in charge 1 is equals to what? KQ2 over what here? R squared times unit vector. What do you notice here? Generally, we can as well say U1 is what? KQ2 over what? R squared, right? As to find the size of the intensity. What do you notice here? Intensity in charge 1. U1 means intensity in charge 1 can only be experienced by what? Charge 2. So intensity in charge 1 can only be experienced by what? By charge 2. This charge 2 here means what? Test charge. Am I communicating here? Okay. Similarly, look at this. If we are saying that E1 is F over Q1, what do we say is E2? E2 becomes what? The force over what? Somebody? Q2. I will repeat the whole process again. E2 will then be, our force is simply this, right? So let's put our force value. We have K, Q1, Q2 over what? R squared times unit vector times 1 over what here? Q2. I hope you guys know why we say times now. Here will have been divided by Q2. So once we take off that division sign, we have 1 over Q2. So that means that Q2 in this case, we cancel what here? Q2. So our E2 becomes what? K Q1 over what here? R squared times unit vector. So that means that intensity in charge 2 is only experienced by what? By charge 1. Now let's see. Let's see. Please, if you are following, indicate that you are following. And please ensure that you like the video, like our video, like the video and share. Please share. Let's share the video, like and share. Now, we will solve some problems from your textbook, then also solve some past questions. Is that clear? Also solve some past questions. All right, I have a question that says that find the electric field. I hope this is clear. Let me clean up this, right? Please, guys, let's share so other people can join. Let's keep on sharing the link. Let's keep on sharing the link for others to join. Let's share the link for others to join. Okay, a question here says, let me write out the question here. Find the electric field. Find the electric field. Sorry, I have to write at a point 20 centimeter from a charge of 20 microcoulomb, then what force will be? What force will be? What force will the field exert on a charge? Exert on a charge of 5 microcoulomb placed at that point. What force will the field exert at that point? All right, look at this. Question say find the electric field at a point 20 centimeter from a charge of 20 microfarad. Now, in this case, we're not told if the charges are placed horizontal or vertical. So you can just decide if you have to use horizontal or vertical. So I'll just assume a line separated Then I'm going to place my charge here. Find the electric field at a point. So we have 20 centimeter, which is equivalent to 0.2 meter, right? I hope you are aware the unit of distance is a meter. So how do we get this? I have to divide this by what? 100, right? That will give us 0.2. So, okay, at a point, this form a charge. So the charge here is 20. Let me call this the charge, which is 20 microcoulomb. All right. Then, from the charge of this, what force will the field exert? Okay, let's call here a point A, and let's call here point B rather, and here point what? Point A. The charge is located at point A. Then we have to find the electric field at a point 20 centimeter from a charge of this. That means from this point to this point is what? 20 centimeter, which is equals to what? 0.2. Exactly. So what do we do here? Let's find the electric field first. So if we are to find the electric field at this point here, that will give us, in this case, we have a charge. I have a charge here. We are giving, let me list out the parameters given. We are giving our charge to be 20 microcoulomb, which is equivalent to 20 times 10 to the power of minus 6. Micro represent 10 to the power of minus 6. Milli represent 10 to the power of minus 3. Nano is 10 to the power of minus 12. Pico is 10 to the power of what? Minus 9. Then we have what we call the Armstrong, which is 10 to the power of minus 10. But the major one we make use of most at time is micro, milli, and nano. Okay? But just take note of these conversions, all right? So if I have 20 microcoulomb, that means 20 times 10 to the power of minus 6. Is that clear? Which is also can be expressed as 2.0 times 10 times 10 to the power of what? Minus 5 coulomb. Hope you know why it's minus 5. If I'm to move my point here backward, okay, it means I'm going to be adding plus 1 to minus 6. And that will give us what here? Minus 5. You can either use this to solve or use this to solve any of them, all right? Now let's go. So our intensity at point B will be K what? QA over what here? R squared times unit vector. Like I said, if I have this, go back to the lecture, the lecture we just did now. If I have a charge here, Q1, and what here? Q2. Separated by distance R in meter, right? We say the intensity experienced in 1 is what? KQ2 over what? R squared. Is that clear? While the intensity experienced in what? At this point here is what? KQ1 over what? Over R squared. What does that mean is that to find the intensity at this point, okay, from this point here, from this distance here, I have to consider this charge here, right? Which is our KQA. This is our QA. All right. Our distance is what? 0.2. So let's put the value. We're going to have our intensity will then be what? Our K is 9.0 times 10 to the power of 9 times. Our QA is, let me use this to solve. We have 20 times 10 to the power of what? Minus 6 divided by our distance of separation is 0.2 all what? All squared. So let's see what we're going to have. Let me get my calculator. Okay, so let's finish up. Please, in the comment section, you can also solve and let me have your answer. So let's go 9 multiply with 20. This will give us about 180. So our intensity at point B, that will give us about 180 times 10 to the power of 9 minus 6, that will give us 3, divided by our 0.2 all squared is about 0.04. So let's divide 180 by 0.04. 180 by 0.04 is about 4,500. So intensity experience give us 4,500 times 10 to the power of what? 3 Newton per watt Coulomb. Are you there? Okay. So our intensity experience, question say find the intensity, right? Intensity experience. Okay, let me fill intensity. Therefore, the intensity is, let's convert this to the proper standard form. I'll move my point backward. Let's go. We have 1, 2, 3. Is that clear? Let's go again. 1, 2, 3. That will give us about 4.5 times 10 to the power of what? Of 6 Newton per watt Coulomb. All right. Newton per Coulomb. So if you are following, just indicate that you are following. If you are following, indicate that you are following. Please check for me in the comment section. Let's calculate and check as well. Please check. Okay, someone said network. Okay, is bad. Please, if you are following, indicates that you are following. I hope this is clear, right? So the intensity experience is about 4.5 times 10 to the power of what? 6 Newton per Coulomb. Then the second part now says that what force will the fluid exert on a charge of 5 microcoulomb placed at that point? What force will it exert? What force will the fluid exert when a charge of 5 microcoulomb is placed at that point? What does that mean is that if I place a charge here, then we are told that if I now place a charge here called 5 microcoulomb, this becomes the test charge, right? This becomes what now? The point what? Charge. Is that clear? So what force will be experienced here? What force will be experienced here? What force will be experienced here? Okay, when a test charge, when a charge of 5 microcoulomb is placed. This is a very simple case here. Just have to recall. You know, we say that electric field intensity is force per unit what? Charge. The first formula we derive from here, I can cross multiply this, right? That will give us our force equals to what? Q what? QE. So here the first experience becomes, what's the charge? The new charge is 5. 5 times 10 to the power of what? Minus 6. Microcoulomb means minus. Times the intensity experience is simply what? 4.5 times 10 to the power of what? 6. Is that clear? So what we do now is to multiply. We multiply 5 by 4.5. 5 times 4.5. 4.5. This is about 22.5. So the first experience becomes 22.5 Newton. Why do we have to say this? Look at this. The power is minus 6. The power is what? 6. There's a rule here that says when you multiply, you have to just add up the power, right? So multiply this by 4.5. By the time we add up minus 6 plus 6, this and this, the result is what? 0. So that means the result, answer becomes 22.5, okay, times 10 to the power of what? 0, right? All right, 10 to the power of 0, we know is 1. So 1 times this remains what? Remains 22.5 Newton. Okay, so this is just an example from your textbook. Let's proceed further. Example 2. Please, if you are following, indicate that you are following. Example 2. All right, guys, are you guys following? Let's look at another example. Someone saying, "Sir, I did not have direction when we are solving for intensity." Someone commented, "I did not have direction when solving for intensity." Yes, it depends on the equation given. The equation we just solved said, don't forget that we are told that find the electric field at a point 20 centimeter from a charge of 20 microcoulomb. We're not told if it's horizontal or what, vertical. So from the equation, you can just solve direct, ignoring the direction. Are you getting it? You can't determine your direction by yourself when the equation did not specify direction. So please take note. But let me give an example to clear your question just now. Your question. Let's say we are giving this diagram. Let's see, look at this diagram. Giving this diagram, I have a charge here, a charge of 5 nanocoulomb, and I have another charge here, 20 nanocoulomb. Okay, separated by a distance of, let's say, 2 meters, and we have to find the intensity at number 1, the 5 nanocoulomb charge. Number 2, intensity at the 20 nanocoulomb charge. Let's look at this now. Okay, I'll be clear now. Look at this question. We are given this diagram. We are told that we have 2 charges. Let's call that charge A and charge what? B, right? Separated by distance. Distance there is 2 meters. Is that clear? And we also find intensity at what? The 5 nanocoulomb charge. The intensity at what? 20 nanocoulomb charge. Intensity at this charge. Intensity here is experienced by this. Don't forget. Then intensity at point B at 20 nanocoulomb charge is experienced by what? 5 nanocoulomb charge. I hope you're aware. So for the first one, solution. If we are to find the intensity on the smaller charge, which is at point A, is that clear? What's the formula? That will give us K QB, right? Over what? Over R squared. Don't forget. Common mistake people always make in the exam, or if they find the intensity at 5 nanocoulomb charge, you will see some students still be using this 5 to solve. What they are saying is that what is the intensity that emanated from this charge? That means your focus will not be on what? On the first charge. So I gave us a derivations, right? That to find the intensity at a particular point A, formula will be what? KQB over what? R squared. To find the intensity at point B, what will be the formula? EB, right? Equals to KQA over R squared. Please go through the lecture note again. This will really help you throughout your journey. Now let's go. So intensity at 5 nanocoulomb charge is definitely this, right? And that will give us what here? Let's solve this. Our EA becomes, our K is 9.0 times 10 to the power of 9. Our QB is 20 times 10 to the power of what? Nano is minus 9. Don't forget, right? Nano means what? Minus 9. Okay. Then divided by R squared. The distance separating them is 2. So we have what here? Here will give us 2 squared. 2 squared. So let's finish up this. So intensity at point A becomes, if you are following, indicate that you are following. Let's go. We have 9.0 times 20 should be about 180, right? 180 times 9 minus 9 is 0. So let me just take off this, right? So when you divide this 180 by 4, what we have as a result? The result there is 45. So intensity at point A is simply 45 Newton per watt per coulomb. Now, it is in this kind of question that we can now talk about the direction. Do you know why? We are told that we are given a system of charge like this along the horizontal. Exactly. In vector, S-axis, a vector can either be 2D, right? 2D vectors or 3D vector. A 2D vector is a vector that has X and what? And Y as, right? A 3D has X, Y, and Z. Is that not? Under Coulomb's law, we are only considering what? 2D. 2D, meaning X and what? And Y. So this is called Y axis. This is called negative Y. This is called negative X. Don't forget that vectors are represented as, let's say if I have vector A, I can represent vector A as what? As Si plus what? Yj. This is for 2D. Then for 3D, we're going to have Si plus what? Yj plus what? Zk. Exactly? So that means that the S-axis represents what? The I component, the I direction. Here is what? Minus I. Exactly? This is called plus J. Exactly? This is called what? Minus J. This is also called plus I. So anything S represents I. Anything Y represents what? J. Okay. Now, look at this now. Intensity at point A simply means that the direction of action is going towards what? Point A. Find the intensity at point A. Find intensity at point A, meaning from 2 to what? To 3. Are you getting the concept here? Intensity, the force of attraction is coming this way. If this is my test charge, if this is my test charge and this is my point charge, is that clear? There will be a graph. It's like saying there's a burning bush. If I have a burning bush, the more you are coming close, the more you are, it's as though you are experiencing the influence of the force towards what? The burning bush. Is that clear, somebody? So when I say find the intensity at points at 5 nanocoulomb, all right? What is the intensity there? Let me explain one or two things. Let me clean up this. Just have it in mind that your Y represents your J, your S represents your what? Your I. All right? So let me explain. Please take notes. Take note, guys. Take notes. Take notes. Take notes. If I have this, I have a charge here. Charge 1, and I have charge 2 here. And I'm to find my intensity in 1. Intensity in 1 becomes what? 1,2. Are you there? 1,2 means from 2 to what? To 1. The formula here would be K Q2 over what? R square. Don't forget that if I'm to find the intensity in charge 1, I will consider. But the idea is that intensity in charge 1 can be expressed as what? E1,2. Meaning 1,2 means the direction of action. Intensity is a vector quantity. It has direction. There must be a direction. There must be where the intensity is pulling you towards. Like I just explained using a burning bush, right? So there will be a pull because if I'm to find the intensity here, the force here, the electric force here, few lines here, right? We drag this charge towards this direction, which is 2 to what? To 1. But for me to find the amount of intensity here, how intense this, I'll consider what? Charge 2. Now, so that means for this kind of intensity, which is from 2 to 1, my direction will be minus I. Why is it minus I? Because we are moving towards negative S direction. Don't forget that I say that this region represents what? Minus I, right? This was somebody plus I. This was plus J. This was minus J. Don't forget. So when the intensity is towards this side, it means the direction is what? Minus I. And minus I means towards the negative S-axis. But if I'm to find this, what about this? Now tell me in the comment section. If I'm to find my intensity in chart 2, intensity experience here what would that be? That's going to be 2 comma what 1. So if I'm to find my intensity, okay, at this point here, the formula becomes what? E21, meaning from 1 to 2. So the reverse will not be the case. The graph will not be towards this direction. But the formula here will be what? Will be KQ1 over what? R squared. R squared. Are you there? R squared. All right? Okay. So that is just for this. R squared times unit vector of 2 comma 1. This one here, the unit vector is what? 1 comma what? 2. Exactly. But the distance between the distance between charge 1 and charge 2 is what? R squared, right? Is R rather. So the direction of action for this, for E21, which is from 1 to 2, from 1 to 2, from 1 to 2, will be positive I. Exactly. Now look at this question here. The question now says that the question is saying that find the intensity at this. We have seen that intensity at this, which is what? Our EA, right? Is given as what? KQB over R squared, which we have gotten the answer. The answer is this. What then will not be the direction? What then will not be the direction? Since I'm looking for the intensity at this point, it means my direction is towards minus R. So direction is what? Towards what? Towards the negative x direction. Towards the negative x what? Axis or direction. Exactly, somebody. Please, if you are getting this, indicate in the comment section that you are following. Please indicate. Please indicate that you are following. This will really help me a lot to know what to do next. Please, are you guys following? Just indicate. I will solve number 2, then I will give us some other things to take note of under intensity. Intensity is very simple, but if you don't understand some of these things, you might just feel you are not getting it. These are just some secrets I'm sharing. All right. Now let's solve. Let's solve the second one. Let's solve the second aspect. The second one says find intensity at what? At discharge, meaning at this point, right? So intensity, which is our EB, intensity at EB is going to be what? KQA over what here? R squared times our unit vector. Exactly. So that means our intensity at point B, at this, will give us 9 times 10 to the power of 9. Our QA is 5 here. 5 times 10 to the power of minus 9 divided by our distance is 2 squared times, what do you think will be our unit vector? That will be I. Why is it I? Why do you think it's I? Let me show you. Intensity at point B. At point B, the direction of action is towards this direction. All right? It's towards this direction. So that means that we are considering that the intensity is here. So the direction of action is towards this direction, which is our positive what? I. But let's solve what? Let's finish our calculation and all that. Okay, if you are following, indicate. Thank you so much for following. Thank you. Okay, so let's finish up. Our EB becomes 9 times 45. That will give about 45. Right? 45 divided by 4, because 2 squared is 4. Then we have here times I. Sometimes you must not indicate this I here, but you can indicate so that you don't forget to write out the direction. All right, so 45 divided by 4 give us about 9. So our EB is simply 9I Newton per Coulomb, but our EB, the intensity here, is actually 9 Newton per Coulomb. This I here represents the direction, right? This is what I would have done with the first example, which is this. I would have just put my minus I for this first one. Don't forget. So direction here becomes what? Towards what here? Towards the positive what? Positive x what? Direction. That is answer to this. Now there's something I want to show us briefly. I would like to show us something briefly so that we can take note of. Very important. Okay, let's take note of this. Very, very important. Look at something. Let's say if I have this. If I have 2-point charge here, I have Q1 and Q2 separated by distance R. To find the intensity in one, we agree that the formula is what? KQ2 over what? R squared. Is that clear? Good. This is also equivalent to, times rather, unit vector. If they say intensity in one is same as what? E1, 2. Intensity in one simply means from charge 2 to what? To 1. The direction of action from here to here. I'm looking for intensity here. Intensity here is felt by this, so it will come this way. Is that not? But while solving, I will use what? Charge 2 to solve, which is why we are using charge 2. Is that clear, somebody? So for this question now, we're going to be having here to be at 1, that will give us 1, 2, right? 1, 2. Is that clear? Okay, let me start by saying E1 is equals to what? E1, 2. Is that clear? So that means that our E1 will then be what? Q what? Q charge 2 divided by R squared 1, 2 times unit vector of 1, 2. For this, our E1 becomes what here? KQ1, KQ2 divided by what here? By R squared 1, 2 times the unit vector, direction of action of this vector is from 2 to 1. Don't forget, from 2 to 1. 2 to 1 means we are going towards what as this? Minus I. Is that clear? So I'm going to put minus I here. So then our E1 is will be what? Minus KQ2 divided by what? R squared 1, 2. This minus sign here actually indicates the direction, meaning minus I. Don't forget, minus what? I. Okay, so let's look at this. For E2, what then do you think will be E2? E2 means find the intensity at what? At charge 2. That will give us what? E2 equals to what? E21, meaning from 1 to 2. For E2, I'll consider charge what? Charge 1. So our E2 becomes what here? KQ1 over what? R squared 2, 1 times unit vector of what? 2, 1. So our E2 become what here? KQ1 over what? Over R squared 2, 1 times what will be the unit vector? What will be the direction of action of this force, electric force? For 1 to 2, this way. Okay, this way, plus I. So here will be what? Plus I. Is that clear? So take note of this, very important. So this I represents the direction. Let's say, for example, if I have my E2 to be, let's say 5I, that means my E2 absolute magnitude or size is what? Is 5 Newton per Coulomb. If I'm to remove 5 from 5I, what will remain here is I. This I means plus I. So that my direction will then be what? Plus I, right? And plus I can be interpreted as what? Positive S direction. Exactly. So for this, if I'm to do the same thing here, let's say I have minus 5I. Don't forget that my E If my E1 is minus 5I, my E1 absolute is what? Is 5 Newton per Coulomb. If I'm to remove 5 from here, what will remain here is what? Minus I. Minus I means what? Towards the negative S what direction. This is just how to interpret the size and direction of an electric field. Alright, electric field strength. Okay, let's see something else. What if I have two charges this way? I have a charge 1 here and I have charge 2 separated by a distance. Let's say this time around they are along the vertical axis. The same thing. The same thing. Vertical here means J, right? Minus J. Just the same thing. And we have to find let's say we have to find our E1. Find E1 and what? And E2. To find E1 will be what? KQ2 over what? R squared times unit vector, right? Unit vector here will be, don't forget that our E1 is E1, 2. So I will consider charge what? Charge 2, right? So to find E1, that will give us KQ2 over R squared times unit vector. This unit vector, what do you think that will be? What would that be? From 2 to 1. Meaning I'm going upward, right? From 2 to 1 means towards positive J. This means positive J. So here will be what? Here will be KQ2 over what? R squared. Let me just substitute, remove this. I'm going to have plus what here? Plus J. Is that clear? For the distance here will be what? Will be 1, 2. Don't forget, 1, 2. Now, what about if we are considering our E2? E2 will be what? KQ1. Okay, E2 is going to give us E2, 1, right? So that means our E2 is going to be KQ1 over what here? R squared 2, 1 times unit vector of 2, 1. So electric field at point 2 will give us what here? KQ1 over what? R squared 2, 1 times. What will be the direction of action? Our direction of action, what will it be for 1 to 2? For 1 to 2 means towards what? Negative J. So I'm going to have minus J here. So I can write this as E2 equals to what? Minus K Q1 over what here? R squared 2, 1 times what here? Times J. That's just it. Okay. Please, if you are following, indicate that you are following. Okay, someone corrected us on something. I'm so sorry for that. 45 into 4 is 11.25. Thank you. 45, right? Into 4 is 11.25. I think that was in the second example, right? Multiplying 9 by 5 divided by 4. Is that not? Okay, so please take note of this. Thank you for that. Thank you. Thank you for that correction. All right, so let's look at what if I have in a system of 3 charges. Now, this is what I want to. What if I have a system of 3 charges? If I have this, I have Q1, I have here Q2, and I have here Q3. The distance between charge 1 and charge 2, let's call it A. Distance between this A, this is what? B. And now we have to find E1, over 2, find E2, over 3, find E3. Listen, this is a more tougher or tough example, tough case you have to take note of. We have 3 charges. We can have more than 3. We can have like 4. The intensity is not always between two charges. If we are giving Q1, Q2, Q3, and we are asked to find E1, E1 means what is the intensity at charge 1, meaning that charge 1 it has more intensity. It means that the emphasis rather is on charge 1. The intensity in charge 1 will be experienced by what charge now? By charge 2 and charge 3. If I have only two charges and I say find the intensity here, I will say the intensity here is experienced by this, Abi. If I have this and I say find the intensity at charge 2, intensity at charge 2 will be experienced by what? Charge 3. What about a case like this? That we asked to find the intensity on a particular charge over other two charges, like this system. Let's go. Now, there is a principle called superposition of forces. Superposition of what? Of forces. Of forces or electric what? Forces. Now listen. The intensity experienced in charge 1 at charge 1, according to superposition of forces, is equals to what? E1, 2 plus E1, what? 3. Meaning the direction of action must be from 2 to 1. If it's just between this, we'll say from 2 to 1, right? Now it's not between 3 charges, meaning from 2 to 1 and from 3 to 1. To find the intensity here, it means I'll consider from here to here, also from this to where? To this. And where do you think is the direction of action? They are all towards negative what? I. In my Cartesian diagram, this is negative I. So they are all coming towards negative I. Is that clear? Okay, so let's analyze this. This will then be our E1 equals to what? To find E12 means I'm looking for intensity in charge 1. I'll consider what? Charge 2. E13 means I'm looking for intensity in charge what? 1. I'll consider charge what? Charge 3. Is that clear? So that will give us what here? K Q2 divided by, okay, distance between charge 2 and charge 1 is A. So I'll put what here? A squared. Then minus I. I hope you know why we're using minus I here. The formula we say is what? We say E equals to what? KQ over R squared times unit vector. So I've defined my intensity, I've defined the charge, I've defined the distance, then I'm defining what now? The direction of action. Meaning where is the action acting towards? They're all acting towards charge 1. So towards the negative I. Okay, so I'm done with this one. So we have plus. Let's consider this. What about E13? E13 will be K Q3, right? All divided by what? From 3 to 1, the distance covered is both A and B. So here will be A plus B all squared times minus I. Don't forget, times minus I. Alright? Distance covered from 3 to 1 is A plus B. So I will add up the distance together and square. So let's rearrange this. It means our E1 is then equals to what? Minus I times K become minus K Q square I, right? Over what? Over A squared. Minus times plus give us what here? Minus K Q3 over what? A plus B all to the power of 2I. Are you there? Okay, so take note of this. Take note of this. This is our formula for finding intensity. So what we do is that if we are not giving Q1, Q2, Q3, you can put the value of your Q2, put the value of your A, of your distance, right? Subtract it from whatever you have here. Your answer will still be in I. So any value you have is the size of the intensity experienced at charge 1, is the size. Then the value of I will now tell us the direction, which is towards the negative S what? As is towards this negative. It means everything is acting this way. What if we are also find? Okay, number 2 now says, number 2 says, look at it here. Find E1. I've done for E1, right? Let's solve for E2. E2 will now be, what will be E2? If E1 is E12 plus E13, E2, that means all of these force here. Let me remove this now and show you. It means that my direction of action, we're not considering E2. It means from 1 to 2, then from 3 to what to 2. Is that clear? So E2 is the one that has the intensity. I'm looking for the intensity here. So to be that the direction of action, okay, of the field lines will now be from charge 1 to charge 2, then from charge 3 to charge, which will give us E2, 1 plus E2, 3, meaning from 1 to 2, from 3 to 2. Don't forget that if I'm to find my E21, I'll consider charge 1. Yeah, I'll consider charge 1, 3. So let's put this together. Our E2 becomes what here? Here we have K Q1 over distance between charge 1 and charge 2. Charge 1 and charge 2 is still A. So I have what here? A squared. Now, what do you think is the direction of action? We're looking at from 1 to 2. From 1 to 2 is plus I, right? From 3 to 2 is minus I. Don't forget. Here we have what here? I plus. So our E23 will give us what here? KQ3 over what? Distance between charge 2 and charge 3 is simply what here? B squared times the direction of action from 3 to 2 is towards the negative I. Here becomes minus I. So our E2 becomes what here? KQ1 over A squared I minus times plus give us what here? Minus KQ3 over what here? B squared I. The same thing can be repeated if we have vertical. Just repeat the same thing. So I won't go into vertical. It's the same thing. In vertical, we are not considering the J component. Exactly. Okay. Now, what about why I'm going through this process? Because there's a question I want to solve from your textbook, which keeps on repeating itself almost every year. For those of you who are in IMSU State University, every year, every time, even last year, it came out to, I think, during the test, one of your tests, some years ago, it came out in the exam. So it might likely appear again, possibly maybe in your exam or during your test. So let's just solve and see what we can get from there. But there's something I want to show before we solve that. Please, if you are following, indicate that you are following. Please indicate that you are following. Please indicate that you are following. Indicate that you are following. Let's look at inclined. Inclined. If I have charges that are inclined, if I have an inclined plane like this, please pay attention, guys. This is very important. And I have my charge 1 here, I have my charge 2. I have a distance of separation, which is in meter. Are you there? Let's say the distance from this point to this point is A, and distance from here is what? Is B. And we are asked to find the intensity in 1 and what again? And intensity in what? Find 1, E1, number 2, find E2. Let's look at this. If I'm to find the intensity in charge 1, that means the intensity in charge 1, that will give us E1, 2. Don't forget, right? Meaning from 2 to 1, from this 2 to 1. Are you there? From this 2 to 1. But if I'm to solve this, my direction of action will not be like that of horizontal or vertical. Is that clear? If I have this, if I'm to find my charge 1 and my charge 2, if I'm to find my E1, I will say from this, right? That means minus I. But in this case here, we have an incline. So the same concept we use here cannot be used, okay? Completely cannot be used here actually because I don't have any third charge here. If I have a third charge and I'm to find the intensity of this charge with this, I can consider that because this is along the vertical. I can also consider that along the horizontal. But if when two charges are inclined, I can't consider that. I can't just use I and J. I have to bring up the concept of unit vectors in physics. But just take note that E1 is what? E12, which is equals to what? K Q2 over what? R squared 1, 2 dot unit vector of what? 1, 2. Just take note of this. Now, before we find our direction of action, I have to look for the value of this R using what we call the Pythagoras theorem. This is a right angle triangle, right? And to find the other side, the longest side, we use the Pythagoras theorem. So I will say using Pythagoras theorem, using Pythagoras what? Theorem to find the distance. Because distance here is R12, meaning what is the distance between charge 1 and charge 2, which is this. So let's find this longer, this length here. Okay, let's find this length. So to find the length here, that will give us R squared equals to what? A squared plus what? B squared, right? The square of the hypotenuse equals to the square of adjacent plus square of the opposite. If we are considering an angle called theta, right? This becomes the opposite, becomes what? The adjacent. So the rule is saying that R squared equals to A squared plus what? B squared. So from here, the value of R becomes what? Square root of what? Of A squared plus what? B squared. Are you guys following? So if that is the case, so that means that we can actually find our direction of action. So direction of action 1, 2. Let me just find this. Now we have defined this. Let's find our direction. Meaning from 2 to 1, from 2 to 1, from this charge 2 to this charge 1. But while moving, I will not move along this line, along this plane here, along the hypotenuse. I will not move along the hypotenuse line. My movement must be from this point here to this point. It means I'm going this way. Then when I get to this point, I will divert this way. Because the direction of action says from charge 2 to charge 1, meaning from this region, I will get to this point to this region. Similarly, for that of E2, to find our E2, okay? To find E2, which is E21, meaning from 1 to 2, I will come this way and this way. I will come this way and this way. All right? Don't forget. But let's define R12 first. From charge 2 to charge 1. If I'm going downward means negative J. Don't forget. This other way means what? Negative what? I. Downward. Look at it here. Downward is what? Negative J, right? And when you divert, it means negative I. Negative I, right? This is negative I. This is what? Negative J. So by the time we are moving downward, we are moving towards negative J first in the Cartesian plane. Then when you divert, it means we are moving towards negative what again? I. Now let's combine both and see. So listen, just pay attention. So if we are moving this way, it means negative J. That negative J times this B will give us what here? Minus BJ. Please take note. We move downward, right? That is minus J times B minus BJ. When we move this way, that is minus I times A is what? Minus AI divided by square root. Let me show you something. The unit vector in physics is simply vector R divided by what? Modulus of that vector. Don't forget. For example, let's say if vector R is Si plus Yj, the unit vector, which is our arrow cap, which is this, is equals to what? Vector R, right? Meaning I'll repeat my vector R, Si plus Yj, which is this, then divided by what here? We are assuming that we are given this. So if I'm giving this, I'm to find this. The rule says divide that vector by the modulus. So modulus simply means square root of S squared plus what? Y squared. Let's say, for example, if I have vector R to be equals to 3, let's say 3i plus 4j, for instance, I'm to find my unit vector R. Formula says what again? Vector R over what? R modulus, right? So that will give me what here? Unit vector becomes What's that vector R? 3i plus what? Plus 4j, right? Over unit vector of R becomes what? Square root of what? We say x squared plus y squared. What's that x here? It's 3 squared, Abi. Plus what here? 4 squared. Are you guys following? So by the time we add up, this will give us what here? Arrow cap equals to 3i plus 4j divided by square root of what? 25. Of course, because 3 squared plus 4 squared is 25. The root of 25 is what? It's 5. That will then give us 3i plus 4j divided by 5. Exactly. So the same thing, the same concept here is that the direction of action is from 2 to 1, meaning from this 2 to 1. And we have defined the vector. This is our vector. This is like saying the vector R, which is this, right? Or which can be represented as this when we have numbers. Is that not? So the next is to find the modulus. The modulus will now be what? Minus b, right? All squared, which is this, plus minus a, all what? All squared. Don't forget. So by the time we solve for that, this becomes what? Our unit vector 1, 2 becomes minus bj minus ai divided by square root of what? Minus b all squared is what? Is b squared, plus minus a all squared is what? Is a squared. Minus b all squared is b squared. Minus a all squared is a squared. I hope you guys are aware. Minus a all squared is same as minus a times minus a. Minus times minus is what? Is plus. What's a times a is a squared. The same thing happens to what? Minus b. Minus b all squared is what? Minus b times minus b. Minus times minus is what? Is plus. B times b is what here? Is b squared. Are you guys following? So that is for this. So we have defined what this value represents. Therefore, our E1 will then be what? K Q2 divided by what there? R square 1, 2 times the unit vector is now this, right? Minus bj minus bj minus ai divided by square root of b squared plus what? A squared. But our distance between charge 1 and charge 2, our r square 1, 2 is simply this, right? So I can repeat that as, let's repeat it here. Our E1 becomes what? K Q2 over the distance here is square root of what? Okay, I can just repeat it here. Let me just put it here. R12 is this, right? So let's just replace the whole of this here. That will give us square root of a square plus b square, right? A square plus what? B squared. All what here? All squared. Don't forget. So from here, square can cancel square roots. So we are going to be left with what here? A squared plus what? B squared multiplied by what? Minus bj minus ai divided by square root of what here? B squared plus what? A squared. You can stop here. Then all you just need to do is to substitute your value. But I can still continue. I can evaluate this. The whole of this can be half, meaning a squared plus b squared all to the power of half. Then this can multiply this to give us 3 divided by 2. But you can just stop here. This is also good. It makes your evaluation also simple and all that. So please take note of this. Please, if you are following, indicate that you are following. Please, if you are following, indicate that you are following. Please indicate. Okay, let's find our E2. Let's find our E2 intensity. Oh, I'll explain the diagram, but I will repeat it again. Okay, here we have the diagram, right? We have this, we have our charge 1 here, our charge 2, and here's A and here's B. This is our distance in meter, and we are looking for the intensity, right? We have to find our E2 according to what we have learned so far. Our E2 is same as what? E21, which is equals to what? KQ1, right? KQ1 over what? Yeah, over R squared 2, 1 times unit vector of 2, 1. Don't forget. So yeah, we're going to have here to be. Let's define our direction of action, our unit vector 2, 1, which will give us from 1 to 2, from 1 to 2. It means this way I'm going this way, then this way. This way is what? Positive I. This way is what? Positive J. Exactly. So we are going towards a positive S direction, then followed by what? Positive J. So that means that positive I times A is AI, right? Positive J times B is plus what? Bj divided by modulus of that vector. Formula for unit vector says that the vector over the modulus of the vector, that will give us A squared plus what? Our value of A and B is positive, so that will give us A squared plus B squared. Is that clear? So we can combine both together. We can combine both together. Please take note of this. From here, our E2 will then be KQ1 divided by the distance between charge 1 and charge 2. We have already defined it using the Pythagoras theorem as square root of A squared plus B squared, all squared, right? Times. Then our direction of action is simply this, right? So let's just put this here. That will give us what? We have AI plus what? BJ divided by square root of what? Of A squared plus B squared. This can go with this, right? So our E2 becomes what here? Becomes KQ1 divided by here. This will give us A squared plus B squared times AI plus what? BJ. Okay, divided by what here? You know, I said I can stop this way, right? But let me show us what I tried to express in the first one. Is that I can express this as my A squared plus B squared, or the raised to the power of minus, so raised to the power of what? Half, rather. A squared plus B squared raised to the power of what? Half. The whole of this is raised to the power of 1. Are you aware? So according to the law of indices, if I have a common base, I can pick one of the base and add up the power, right? These two, they have the same base. The power here is 1, the power here is what? Is half. So 1 plus half give us 3/2. So my E2 will then be what? KQ1 divided by A squared plus what? B squared, all to the power of 3 divided by 2 times what we have here. We have in brackets AI plus what? Plus BJ. So anyone, you can either stop here or you can stop here. Alright? While solving, I think the best is this. The best is in this form where we have square roots. So I can just find the square root of anything here and evaluate. Is that clear? Okay. Now let's solve real problem from your textbook. Real problem from your textbook. Okay. We're going to look at one example, then we'll shut down this class. Then we'll continue tomorrow. Tomorrow's class will be on capacitance and dielectrics. Alright? Then after that class, we'll go into DC, direct current. We'll look at Kirchhoff rules and some other principles there. Okay, I have a question here from your textbook that says that a positive charge Q1 equals 8 nanocoulomb is at the origin. I think I have to write it somewhere, but his quite lengthy. Let me just turn right so we can solve. A positive charge Q1 equals to 8 nanocoulomb is at the origin. And a second positive charge and a second positive charge Q2 equals 12 nanocoulomb is on the x-axis at x equals to 4 meter. Number 1 says find the net electric field at a point P. Find the net electric field at point P on the x-axis at x equals to 7 meter. Question 2 says find the electric field at point Q. Find electric field at point Q on the y-axis. At y equals to 3 meter due to the charges. Please, if you are online, indicate that you're online. Please indicate that you're online. Let's look at this question. Okay, guys, some part is cutting off. Please, if you're online, still indicates that you are online. Okay, we are told that a positive charge Q1, 8 nanocoulomb, is at the origin. The word origin means that in the Cartesian plane, it is placed at the point where both x and y is 0, 0,0. That's what the word origin means. And a second positive charge Q2, which is equals to 12 nanocoulomb, is on the x-axis at s equals to 4 meter. Questioner says, find the net electric field at point P on the x-axis at s equals to 7 meter. Number 2 says, find the electric field at point Q on the y-axis at y equals to 3 meter due to the charges. Due to what? The charges. Now let's look at this question together. Okay. The first one says a positive charge Q1 equals 8 nanocoulomb is at the origin. So if I have my Cartesian plane in this form, the origin means the center, right? So our Q1 is here. My Q1 is somewhere here. And Q1 is what? Is 8 nanocoulomb at the origin, meaning it's at the center here. This is my y, this is my x, so it's at the center where both x and y is what? 0. And a second positive charge Q2, which is what? 12 nanocoulomb, is on the x-axis at s equals to 4 meter. Meaning from this origin here, I extend this way, right? 4 meter. We're only placing our second charge here, which is Q2. And Q2, we are told is what? We are told that Q2 is what? Q2 there is 12, right? 12 nanocoulomb. I repeat again, a positive charge Q1 equals to this is at the origin, meaning here the value of x and y is 0, the starting point. Origin means starting point. And a second positive charge Q2, 12 nanocoulomb, is on the S axis at s equals to 4. This is our S axis, right? I will just measure from the origin 0. Measure, bring out our 4-meter distance apart, then place the second charge here. Question answer says, find the net electric field at point P at a certain point P, still on the S axis, right? At s equals to 7 meters, meaning I will extend this line a little bit forward. If from here to here is 4, all they need is that from the origin to that point P must be what somebody 7 meters. So here we have only gotten 4 meters. What number will I add to 4 that will give me 7? Is simply what? 3 meters. So from here to here is what? 7. Don't forget, find the net electric field at point P on the S axis at s equals to 7 meters. So they made the whole thing easy for us. We are told that the first charge is at the origin. So from the origin to here is 4 meters initially. Then I'm looking for the electric field at this point. S equals to 7 meters. All we don't need to do is to extend. I won't create another 7 meters here. No. If you do that, you have failed the equation. So we are told that the first charge is placed at what? The origin. So to find the total length here, I will consider what is here first. I will just add what? 3 meters. And that will give us what? 7 meters. Now let's find the first question. So let's call here point 1, Abi. This is point 2. Let's call here point what? Point 3. Question now says, find the net electric field at this point P on the S axis. This is a very simple question. Let me repeat my diagram here for this example. My charge 1 is 8, right? Nanocoulomb. Our charge 2 is 12 nanocoulomb. Then from here to here we have 3 meters, right? Which is our point P. We call here what? 3, right? This is what? 4 meters. 4 plus 3 is what? 7. Let me just repeat it like I need the side of the box to solve. So to find the electric field at this point, I mean I'm looking for my E3. Exactly. What do we say will be the result here? According to superposition of forces, that E3 is equals to what? E3, 1 plus what? E3, 2. Exactly. So what do we do here? Let's find our E3, 1. E3, 1, that will give us what? KQ1. Don't forget. KQ1. Right? Divided by what? Our R squared 3, 1 times unit vector of 3, what? 1. So let's impute our values. Our E31 becomes, our K is 9 times 10 to the power of 9. Our Q1 is 8, right? That's 8 times 10 to the power of what? Minus 9, right? Divided by distance between 1 and 3. 1 and 3, the distance is 7. When you add up these 3 plus 4, what do you have here? We have 7. So you have 7 all squared. Now the next thing is to determine the direction of action. Will it be negative I or positive I? Since I'm looking for 1 to 1, E31, meaning from 1 to 3. From 1 to 3 means the direction of action, they're all acting towards positive I. Don't forget, towards positive I, this way. The direction of action is going this way. So here will be what? Plus I, right? Okay. Please, if you are following, indicate that you are following. If you are following, indicate that you are following. So here, let's verify again. Our K is 9. Our first charge is 8. So 9 times 8 is 72. So our E31 becomes what here? 72 times 10 to the power of what? 9 minus 9 is gone, it's 0. So this is like saying 8 plus 0, right? I divided by 7 square is 49. 7 square is 49. So by the time we divide this by 49, we're going to be having 1 what we have here will be our E31 becomes what? 1.4694I. Is that clear? 1.4694I. Okay, that will be the our first value. Okay, so we have gotten that, right? So the next is to find, this is not all about the answer. Don't forget that we apply the principle of superposition of forces. That E3, the electric field at that point 3 at point P is equals to E31 plus E32. So we have gotten our E31 and that gave us 1.4694. That is not all. We have to find our E32. So to find E32, this will give us what? Okay, Q2 over what? R squared 3, 2 times unit vector 3, 2. So electric field, which is E32, becomes, our K here is what? 9 times 10 to the power of 9. Our Q2 is this, right? Which is 12 nanocoulomb, meaning 12 times 10 to the power of minus 9. All divided by distance between 2 and 3. 2 and 3, okay, is 3 squared. Don't forget. Then what will be the direction of action from 2 to 3 is still towards negative, it is towards a positive I, rather. Positive what? I. So let's move on again. So we have 9 times 12 is 108. So E 3, 2 is 108 times 10 to the power of 0. Right? Over what here? Here we have I divided by 9. So divide this divided by 9. Our E32 is simply 12. 108, 10 to the power of 0, we all know is 0, right? Just like we did here, this is 0, 0. So this is 1, rather. 10 to the power of 0 is 1, right? Like this also. The same thing also applied here. So when multiply 1 by 108, divide by 9, that will give us 12, 12I. So our intensity from 2 to 3 is 12I. So what do we do next now? Since we are saying that our E3 is what? Recall that E3 is E31 plus what? E32. So that will give us our E31 is 1.4694, 1.4694I. Our E32 is what here? Is 12I. By the time we add up this together, for 1.4694, give us about 13.4694. Okay, yeah. 13.4694I. Is that clear? Or we can approximate this to be what? 13 point what? 47I. Okay, that is not just all. This simply means that the size of the field strength is 13.47. The direction is towards positive what? X axis. Okay, please take note before I explain the board. I hope this is clear. I hope this is clear. I hope this is clear, right? I hope that is clear. I hope it's clear. So let's proceed. Let's proceed. So where we can see that the size of the field is the absolute value, simply means I will neglect the sign, this I, right? That goes 13.47 Newton per coulomb. Then the direction becomes towards the positive X axis. That is our direction. Don't forget that even if I have minus 13.47I, the value of our field intensity, when you take the absolute value, is still 13.47, but just that the direction will not be towards the negative X direction. If here is minus means the direction is towards the negative X direction. When I say take your absolute value, meaning that let the answer be positive. You get? Okay, so let's finish up. We are done with the first part. The second part is what we want to consider. After this, I will end my class. Then we'll continue tomorrow. Now, listen. The second part says, I will repeat this again because there will be a need for us to redraw the diagram. We have told that we have the first charge here, right? Q1, which is 8 nanocoulomb. The distance here, our Q2 is here, right? The distance here is what? The distance here, Q2, is 4 meter. Q2 is, okay, and the second charge is on the x-axis. Okay, 4 meter. Yes, 4 meter. All right. We have a point here called point P, which is 3 meter from the first question. Then we now say find E. Okay, here is 3, total is 7. Oh, good. So find E at point Q. Now we have another point Q. No longer at point P. The first one we solve is at point what? P. We are done with this. Now say at point what? Q. On the y-axis. On the y-axis, meaning I will now move upward. Generate how many distance? At what distance? 3 meter due to the charges. Find the field strength, electric field strength at point Q on the y-axis, meaning from this origin here, I will just generate 3 meter, right? 3 meter, and call here what? Point Q. Are you there? Point Q. Okay, but let's say due to the charges, not due to this point. Are you there? I can only find field strength due to charges. So that means I'll generate a straight line connecting these 3 charges. So I have one here, I have a charge here, and that charge here. So due to the intensity, there's no charge here, this is just a point. I hope you're aware. So there's no way of me coming this, I can't come this way. It's not possible because I don't have any charge here. I don't have any charge here. Okay, the only time I can come this way. Just indicate in the comment section. Hello guys. If you understand what I'm saying, just indicate in the comment section. Okay, I'm sorry for that. I have to change my mic. Now listen, we have done the first one. A positive charge Q1 equals to this is at the origin, which is this, right? And the second charge Q2, is that not? Is on the x-axis at s equals to 4 meter. We are done. The question says find the net electric field at point P on the x-axis at s equals to what? 7 meter, meaning that we have a point here. That's what we did in the first question. A point P, is that not? Where we solve along the horizontal axis. But this question says find the electric field at point Q, okay, on the y-axis. at y equals to 3 meter due to the charges, meaning not due to the point. It means I'll connect these points to this charge here and take off these points, okay? So this point, this is a point we use to find the intensity, all right? The intensity, okay, on those charges. But the point does not, there's no charge. I don't know if you understand what I'm saying. There's no charge there, so I will not include this in the second calculation. So what do we do now is that we have to call here what? R. This remains my point 1, my charge 1, my charge 2. Our charge 2 is 12 nanocoulomb, don't forget. So let's call here 1, 2, and 3. So to find the intensity at point Q, meaning the intensity at this point, what would it be? E3 would be what? E31, E3, 1 plus E3, 2. We're going to use the principle of superposition of forces, right? To find the intensity at this point here on the y-axis at y equals to 3 meters due to the charges. So what did I say? What did we say before now? That before we solve any question like this, we have to find a distance between these points, right? Let's find this distance, the hypotenuse line. Let's find this. Because for me to find my intensity here, we have to consider from 1 to 3, from 1 to 3, and from 2 to 3, meaning from 2 to 3. So from 1 to 3, the distance is 3 meters, right? Then from 2 to 3, the distance is what? We don't know. Let's find the distance. So using Pythagoras theorem, that will give us what here? R square equals to 4 square plus 3 square. Exactly. The square of the adjacent plus the square of the opposite equals to the square of the hypotenuse. So here we're going to have the R squared equals 4 square is 16 plus 9. Let's give us what here? 25. Right? So part of R becomes what? Square root of 25, which is equals to 5 meters. Is that clear? So our distance here is what? Is 5 meters. So let's find our E3, 1. This will give us what? KQ1 divided by what? By R square 3, 1 times unit vector 3, 1. Right? Sure. Okay, so the intensity at this point from 1 to 3, we are considering charge 1. Don't forget, charge 1 is what? 8 nanocoulomb. So let's input our value. Our E31 becomes what? 9 times 10 to the power of 9 times. Our Q1 is 8 nanocoulomb, which is 8 times 10 to the power of what? Minus 9, divided by distance between charge 1 and 3. 1 and 3 is 3. Is 3. So we have 3 squared times. So we are looking at from 1 to 3. In this case here, 1 to 3 is along the vertical axis, not along the incline. It's only 2 to 3 that we consider the incline. And from 2 to 3, don't forget that we say we move this way, then move this way, right? But for this particular diagram, this particular one, which is E31, it simply means from 1 to 3. So we are moving towards positive J. Is that clear? Towards positive J. So in this case here, I will just pick, don't forget what we learned under vertical and horizontal, right? I'll just bring out my word positive what here, J. Don't forget. All right. Or I can also say that with the principle of unit vector that we learned, let's take this. If you are moving up, plus J times 3 is what? Plus 3J, right? Divided by what? Square root of what? 3 square. Is that not? And that will give us what? Plus 3J divided by square cancel square root. Here we have 3. 3 can cancel 3. We are still left with what here? Plus J. You know, I taught you guys under horizontal and vertical. If I have two charges, Q1 and Q2, and to find intensity at this point, it means what? Minus I. Intensity at this point means what? Plus what? Plus I. If I now have vertical, I have Q1, I have Q2. Intensity at this point is what? At charge 1 is plus J. Intensity here is what? Somebody is minus what? Minus J. So for this now, we are going up. We have to find intensity. Find what? E3, right? E3. E3 means what? For the first one, we are looking at E31, which is from 1 to 3, meaning I'm going towards positive J. All you just need is to bring out what here? Positive J. Or if you want to solve this, we can still solve, but you end up having positive J. Is that clear? It's only inclined that we have to consider that principle I gave us. Only inclined. But for vertical or horizontal, if I have this between this now, let's say I'm to find E, if I'm to find E1, 2, what would that be? What would be the direction of action from 2 to 1? I'm just asking. If you're following, please indicate in the comment section. If you're following, indicate in the comment section. I'm so sorry. The network is so bad. Let's just finish up. Let's finish up. Okay, so we have 9 times 8. That will give us 72. We have 72. 9 minus 9 is 0, right? 72J divided by 9. This will give us our E3, 1 is equals to 8J, right? This is the first answer. This is our first answer. So the next is to find our E32. E3, 2. Is that clear? E3, 2. This will give us K Q2 divided by R squared 3, 2 times unit vector of 3, 2. It is in this case we're going to look at the inclined plane now. In this case, we look at the inclined plane because the distance between 2 and 3 is along the incline. This 2 here, this 3 along the incline. So we use the principle of direction of action, right? So let's find our direction of action. Let's find our unit vector. Let's find our unit vector. Then we'll solve. We finish up. Let's find the unit vector. So the unit vector becomes, let's solve this. Our unit vector, 3, 2. That will give us, let's check this out. 3, 2 means from 2 to 3, meaning I'm going this way first, right? From 2 to 3. From 2 means, yeah, we're going towards negative pi. Don't forget. In the Cartesian plane, this way means what? Minus I. Then after then, we're not going towards positive, abi? Positive J. So this way, negative I, positive J. So negative I times 4 will give us what? Minus 4I, right? Here we have plus here. Positive J times 3 will give us what? Plus 3J. Okay? Then divided by, from what we have learned so far, the modulus of this becomes what? Minus 4 all squared plus what? 3 squared. Is that clear? And that will give us what here? Unit vector of 3, 2 becomes what? Minus 4I plus 3J divided by square root of 16 plus 9. So unit vector becomes minus 4I plus what? 3J divided by what? Root 25. This will give us our unit vector equals to what? Minus 4I plus 3J divided by 5. I get this to be about, our unit vector becomes, this divided by this will give us about 0.6 I plus, this will give us about minus 0.6 and 0.8J for divided by 5. Okay, this is 0.6. Okay, so this is 0.8. 0.8I is 0.6J. Can verify for me? When you divide 4 by 5 is 0.8. This minus 0.8, don't forget. Then when you divide 3 by 5 is 0.6J. Let's take note of this. So we have only solved the unit vector, right? So what we do now is to solve the entire E32, right? Let's solve the entire E32. I would like to clean this diagram now. I would like to clean this diagram. Or this part. Let's find our E32. So our E32, becomes equals to 9 times 10 to the power of 9 times our Q2. I guess our Q2 is what again? That 2 is 12, right? It's 12 nanocoulomb. Yeah, 12. 12 times 10 to the power of what? Minus 9. Is that clear? Okay. Divided by the distance between 2 and 3. 2 and 3 is along the line. We got 5, right? We got 5. Don't forget, it's 5. The distance is 5. Okay. So we're going to multiply the whole of this now. Let me write out this first answer. Here we have our E 3,2. We got 8J. Don't forget, it's 8J. It's 8J, right? Okay. So our unit vector here is actually times minus 0.8 plus 0.6J. Is that clear? Okay. So let's finish up this. So 9 times 12 is 108. So we have E3 equals to 108. All right. Divided by what? 25. 25. The distance is 5 there. Divided by 25. This will give us, okay, about times minus 0.8. 0.8I plus 0.6J, right? Okay. So 108 divided by 25 will give us 4.32. So this is E31, right? Sorry. This is our E31, our E32. Okay, E32. Don't forget. So this is the challenge is having a small board. I'm so sorry for that. We have E32. So let's just follow. Let's try and follow. I'm coming. Let me check again. I think there's an error somewhere. We have a diagram like this, right? This is a diagram here. I guess, okay, our chart 3 is here. Our chart 2 is here. Our chart 1 is here. So what we consider here is between this, which is 32. Sorry, E32. I'm sorry for that. So the next one will not be what? E31. So here we are looking for E31. Is that clear? E31. All right. So please let's proceed. So let's go. 108 divided by 25 is about 4 points. So our E3,1 is equals to what? 4.32 in bracket minus 0.8 I plus what? 0.6 what? J. Okay. So what we do next is to multiply this out. So our E31 becomes 4.32 times minus 0.8 will give us minus 3.456I. Then plus 4.32 times 0.6, 4.32 times 0.6 will give us about 2.592J. Then we have to recall that our E3 is equals to E31 plus E3, 2, right? So here we have our E31, which is this, minus 3.456 plus 2.592J. And our E31 is this, plus what's our E32? Our E32 is 8J. So what do we do now? We collect like terms, right? We collect like terms here. By the time we collect like terms, this will give us what? I will add up my J to J, right? So I'm going to have minus 3.456 I, this I, 56I, plus 8J, this will give us plus 10.592J. Okay, 10.592J. So this is our E3 in vector form. Our E3 in vector what? Form. So let's take note of this first. Please, if you are following, please indicate that you are following. Please, if you are following, indicate that you are following. Please indicate. So we can finish up this. If you are following, please indicate that you are following. Okay. So after adding up, we got this, right? We got this. But don't forget that we're going to look for the intensity. The intensity. Okay, you're following, please indicate. I'm so happy. Thank you guys for following. Okay, thank you for following. Please ensure you go through the video again. All right. This board is so small. I'm so sorry. So I have to clean and all that. I know it's affecting majority of you. Now we have solved. The next is to find the magnitude. Intensity. Relative intensity is a vector field, right? It's a vector quantity that have size. I can't just stop here and end my answer. I have to find the resultant in vector. If we are given a vector A to be xi plus yj, and I say find the magnitude of A, vector A, formula says square root of what? Of x squared plus y squared, right? This for 3D. Is that not? This for 2D. If I have a 3D, let's say I have zk, what will it be? Plus what? Z squared. Just like that. Do you get? So the same thing here, but here we have 2D. So to find the magnitude of the size of this, of our E3, what would that be? What would that be? From the comment section, that will give us E3 magnitude equals to square root of minus 3.456, right? Minus 3.456 all what? Squared plus 10.592. 10.552 all what? Yeah, all squared. So let's evaluate that together. We use a calculator. 3.456 squared. Our E3 here, modulus, will give us 11.940 plus, let's look at my 10.592 squared. It gives us about 112.19. All right, 1905. 1905. So by the time we add up this, let's add up what we have there. 11.9440. All right, plus 112.1905. This is about, I guess, please guys will check for me, 124.1345. So let's find the root of this answer. Our E3 modulus, the root here is about 11.14 Newton per Coulomb. 14 Newton per Coulomb. Please guys verify the answer for me. 11.14 Newton per Coulomb. Alright. 11.14 Newton per Coulomb. This is our magnitude. But don't forget that every vector have magnitude and what? Magnitude, right? And direction, right? And direction. So how do we find the direction of this vector of our E3? Look at this now. The final E3 here is not a single vector. We have 2D vector. Is that not somebody? So whenever you have a 2D vector and you have to find the direction, you have to represent the direction in terms of angle. In terms of what angle? We use what we call the directional angle or the standard angle right there to determine the direction of this vector E3. Now let me show us quickly how to find this. Please take notes. I would like to clean the board now. Okay. Let me find. I will just stop at this point and let's find the direction. Now listen. Very important. We're almost done with this class. We're almost done. Okay. The direction, yeah, for the direction, I have to represent the vector, our E3 in vector form, okay, in the Cartesian diagram rather. So look at this, we have negative x. This is minus 3.456i plus 10.592. I have negative I and positive j. Apart from this number here, what we have is minus I. This is what? Plus j. So where is negative I in the Cartesian plane? This is negative I. Where is positive j? This is positive j. That means the value of our E3 will definitely fall in here. We fall in here. Then I can complete my right angle triangle. If you are confused, there's a video we did first semester under complex number. How to analyze the Argand diagram of a complex number. I explain all of this. That's why this class is progressive. You can always go back to complex number. Don't be shy. Don't feel you have outgrown complex number. Just look for the polar form of a complex number in my video and learn. You will see how to analyze direction. I explain it. It's a full video I did. That was first semester. So just note that the value of our I is in this direction. Yj is in this direction. Okay, what about if both of them are both positive? That means our S is here, our Y is here. That means the value of our E3 will now be somewhere here. Do you get the concept here? But there are two angles that will be formed. The first angle is called the reference angle, called alpha. The reference angle. Your reference angle is always along the horizontal components, which can either be negative x-axis or positive x-axis. For example, I said I will not go into this, but let me just start. If my Z, my E3, let's say both of them are positive, and they both falls in here, my reference angle is this. Exactly. I'll just complete my right angle triangle. Let's assume that both of them are negative. Where can we get negative? In the Cartesian plane. This is negative, right? Negative x, negative y. It means it will fall in here. Now the next is to determine your reference angle. Reference angle, like I said, is always along the x-axis, whether negative x-axis or positive x-axis. So I can't put my reference angle here. This is positive. This is what y-axis. So my reference angle is here. So I'll come up this way. Once you can get your reference angle, you can be able to complete your right angle triangle. So what about a case where the value of our E is here? Where do you think would be our reference angle? Of course, is here. It cannot be here because This is x-axis, so I'll complete my right angle triangle. Now, when you find your reference angle, the next is to find your directional angle, which is the major angle you're looking for. For this, what determines the direction of this is your standard angle or the directional angle, not the reference angle, not this reference angle. And the directional angle is the angle measured from the positive x-axis down to the resultant line. What do I mean by that? For this diagram now, we have determined the reference angle, right? Let's find the directional angle, which is our theta. I'm looking for theta now. Directional angle is always measured from the positive x. This is my positive x, Abi. I'll start from here. I will now stop here. Do you get the concept? I will start from the positive x and stop at the resultant line, that hypotenuse line. I will stop there. So the reference angle here, theta, is what? Is 360 minus what? Alpha. Do you understand? Angle at a point, total angle is what? Is 360. So when you remove this alpha, or form this, is that clear? That will give me 360 minus this will give me from here to here. That's my directional angle. Okay, let me give you another diagram. Let's just analyze it together. What about if I have my reference? What's my reference angle? It is there. What will be the directional angle? It's from here to here. I will start from here and end here. This is my hypotenuse. So angle in a straight line is 180. So my theta here is simply 180 minus alpha, reference angle, because total angle here is what? 180. So when you subtract 180 minus this, will give me from here to here. What if the diagram is like this? What if it's like this? Is here. We know the reference angle is there, right? So I'll come up this way, right? Then I will start from here and stop here. So how do we find our standard angle? It's simply 180 plus reference angle plus alpha. 180 meaning from here to here is 180, then plus from here to here. So I'm adding this angle plus this angle to form the what? The standard or the directional angle. So for this now, we know better, right? That is from here to here, which is our theta equals to 180 minus alpha. I know some of you will be asking, what if it falls in the first quadrant? How do we find the standard angle? What if it is here? What if it is here? We know that reference angle is there, right? Standard angle, where do you think it would be? Standard is always measured from the positive x-axis, from here to here. It means from here to here. It means that whenever your value of your vector falls in the first quadrant here, it means that the directional angle theta is equal to what? The reference angle. Where theta is called what? Standard angle, right? Standard angle, standard, or directional angle. Why alpha means what? The reference angle. Please take notes. So throughout our journey, whenever they say find a direction of two vectors, it means find what? Find the standard angle, find theta, not a reference angle. So what do we do here? Since we have seen that our E3 falls in the first quadrant, right? In the first quadrant. Sorry, in the second quadrant, it falls in here rather. So let's find the directional angle or the standard angle. Okay, so before we do that, I've cleaned my vector. Sorry, let me get back the vector. Excuse me. Alright, I just have to go back and get. Now we have told that our x-axis is what? Is simply the x-axis. Okay, let me repeat this diagram again. Let's do it. Here we have the vector falls in here, right? From what we have seen so far. So our x is what? Is 3.456, right? Is that clear? That's our x. That's our x. Okay. Then our y is about, the value is 10.592. Is that clear? Okay. I'm sorry. Let me have to create a space here. Okay. I think this is better now. Okay. So our x is 3.456. Our y is 10.592. There we have our reference angle, right? Here we have what? The directional angle, which is 180 minus alpha. Is that clear? Okay, so let's finish up this. So what do we do now? Don't forget that in the Cartesian diagram, in what we call casts. Cast. The word A means all is positive. In the first quadrant, all means your cosine, your sine, and your tangent are all positive here. They are all positive. Sine means only sine is what? Positive. Cos means only cos is what? Positive. Tan means only tan is positive. Sorry, T means what here? Only tan is positive. So that means in the first quadrant, I can use cos, sine, or tan. In this, I can use only sine. But whenever you use your cosine and your tangent, you must have a negative value. Here, it means that only tangent is positive. It means that your sine and your cosine in this quadrant is negative. This one means that only cosine is what? Is positive. So that means your sine and your tangent are negative. Looking at this diagram, the value of our vector falls in here, right? It falls in this quadrant. It means I will use what to find my alpha? I'll use sine to find alpha. So using sine, if the value here falls in here, it means you can use any of them, either sine, cosine, or tangent. If the value of our E3 falls in here, it means I will use what? Tan. If the value of our E3 falls in here, what should we use? Somebody? Cosine. So using sine alpha. The word sine is from the word so, right? So means what? Opposite over what? Hypotenuse. So here we have sine alpha, which is equals to, opposite is simply 10.592. What's our hypotenuse? Which is 3.456. So sine alpha becomes 10.592 divided by 3.456. Okay, then we have shift inverse of that coming. Sine opposite over hypotenuse. I'm sorry, not over adjacent, over hypotenuse. What is our hypotenuse again? The hypotenuse is this line, right? And we got the answer to be 11.14. Don't forget, this is 11.14. So here we are using sine means opposite over hypotenuse, meaning this over this. So this should be 10.592 over 11.14. I'm sorry for that. So let's divide again. 10.592 divided by 11.14. This is about sine alpha equals to 0.9508, right? 08. So let's find the shift of this sign. Okay. Our alpha, this sine inverse of this, sine inverse of 0.9508. The alpha becomes what here? Is about 71.95 degree. This is our alpha. But this is not our final answer because the standard angle here is theta equals to what? 180 minus alpha. So my theta becomes what here? 180 minus 71.95, right? So here becomes minus 180. We won't be having here to be theta equals to 108.04 or 0.5 degree. If you look at your textbook, for those of you who are in IMSU, you'll find out that The answer, their answer is this. They stopped at 71.95, which is very wrong. Please take note. This angle here in the textbook is your reference angle. Your directional angle is 108.05. Just subtract. By the time you subtract these two, that will give you the standard what angle. Please take note of the correction. In case you are reading and you come across that, so please, I've corrected it for you. In the exam, or this is what you are expected to do in the exam. So I will stop this night. I think we have covered field intensity. Then the next aspect should be electric potential and work done in an electric field. All right, but there's nothing much in those ones. Then after that, we'll now go into points of neutrality in an electric field. I think the next topic should be point of neutrality. Okay, that should be the next topic. Then when we are done with this, we'll go into capacitance and dielectrics. Then when we are done, we'll move into DC, Faraday laws of induction, and so on and so forth. All right. So I would like to end my class now.